Our first speaker is Shiwen Zhang. He's a postdoc at the University of Minnesota, working with Svetlana Mayborota and somewhat with me. And he's going to talk with the landscape theory for discrete Schrödinger operators. Shiwen, you need to unmute. You need to unmute, Shiwen, or I can unmute you.
Can you hear me?
Yes, we can hear you.
Yeah, I was unmuted by you, by all people. Okay, so thanks, Doug, for the introduction. I want to present some of the recent joint work in the wave collaboration on the landscape theory for discrete Schrödinger operators. Okay, let's start. It's a tight bounding model. The domain is a discrete lattice in ZD of size K. We have seen the model in the morning talk. So the discrete Laplacian is given as follows by the standard discrete Laplace. The discrete Schrödinger operator is given as follows by the discrete Laplacian plus the potential V. Take 1D, for example, it has such a simple tri-diagonal form as a K by K matrix. So similar to the continuous case, we can define the landscape function to be the solution to HU equals 1. And the effective potential is 1 over UN. We are interested in using the landscape function and the effective potential to study the spectral property of the original Hamiltonian, especially certain localization property. So the results I want to present are as follows. The first one is some decay estimate for the eigenfunction. So suppose mu phi is eigenpair. The barrier of the effective potential 1 over UN defines such a quantum well with respect to the energy mu. We're expecting the eigenfunction phi to be concentrated in this quantum well. Such results are usually referred to the so-called Agmon type of localization. To do that, we actually need to define the discrete version of the Agmon metric and Agmon weight, which roughly speaking measures the lattice distance to this well, using the weight function given by the effective potential 1 over UN. We are able to show that the eigenfunction phi n decays exponentially with respect to this Agmon weight. So 2 quick remarks. So the results extends what has been previously obtained by the wave collaboration for the continuous case. But the discrete version of Agmon distance is slightly different compared to what's the definition for the Agmon distance on RD. So with this extra log correction, it turns out the log order is the right decay rate in many tight bounding models. Secondly, because of the symmetric structure of the discrete model, so the Agmon type of estimates not only hold true for the bottom part, but also for high energy states near the top of the spectrum. This is done by the so-called dual landscape. And the idea of the dual landscape actually was originated also by the wave collaboration previously by Lira, Filocci, and Mayborota. The results, the main estimates is for deterministic potential. And we actually did some simple computation for the random potential. Say, if our potential is Bernoulli on a 1D lattice, if we look at the first 2 pictures, the blue background here is the effective potential, and the green plot is the ground state. The black line here cuts the first effective well. We see that the ground state sits almost nicely in the first well, as predicted by our theory. This is the ground state story. They're also plotting for high energy states as well as the Z2 lattice, but I think I need to skip the last 3 pictures. Next, we would like to move from individual eigenvalue to the distribution function. So IDS, integrated density of states, finite volume, roughly speaking, it's just the counting eigenvalue counting function per volume for H. using the landscape function and the effective potential, we want to define a new counting function. Given energy mu, we participate our discrete lattice into disjoint cubes of size about mu -1/2. Then we count on how many cubes that the effective potential falls below the reference line mu. And then per volume, this gives us the new counting function. We call it landscape box counting function, n sub u. Landscape law, nu versus n. We are able to show that the new counting function, nu, gives non-asymptotic estimates for the true IDS from above and from below. This is a result, again, for any deterministic potential. But the expression on the left-hand side, we see it's a subtraction of 2n sub u after different scalings. If it is negative, it could be, then it's meaningless or trivial lower bound. Luckily, in many situations that we are interested in, for example, if Vn, the potential is Cantor-Claus or periodic potential, the left-hand side lower bound can be indeed improved as 1n sub u, which is more useful. More importantly, this is also true for the random case, for the random potential. Anderson model, in the sense that Anderson model, the true IDS can be bounded from above and from below by the new landscape counting function, n sub u, after some scaling. This is estimates throughout the spectrum for all energy. If we concentrate it near the bottom for energy near the bottom, the new counting function, using the new counting function, we're able to show that both n and n sub u can be described in terms of capital F, which is the common probability distribution function of the random variable. So such results are usually called Lifschitz or Wishbach-Tell estimates, known for long in physics and math. And these general estimates recover some of the previous known results, also give us some new refinement for different F. Okay, so we may interested, okay, this is the upper and lower bound. We may interested what's the best or optimal scaling constant in such estimates. Especially this inner scaling constant C star actually has something to do with erasure, which will be my last slide. The ratio is the ground state, the first eigenvalue versus the minimum of the effective potential. This ratio has been extensively studied by the wave collaboration in the past several years. For example, the beautiful observation that this ratio is close to 1 plus d over 4 in any dimension. Recently, we obtained some rigorous proof for the one-dimensional Anderson model, actually both for discrete and continuous case, that if you consider this ratio in terms of the maximum of the potential and the size of the domain, if you send either of these two to infinity, the ratio actually approaches pi square over 8, which is about 1.23, numerically close to 1.25, which is the previous guess for the 1D case. But the result depends on the distribution, of course. For example, if you have a uniform random potential, and actually more generally, as long as you don't have a point mass at 0, if you send Vmax to infinity, the ratio does not go to pi square over 8. It approaches 1 instead. This is also true actually in continuous case and actually in any dimension. Okay, I think time is up, and I would like to stop here. Thank you all for listening.
Thank you very much, Shiwen. That was a very clear talk and also well timed. So we have time for questions, and the floor is open. Make sure your mic is unmuted, and just go ahead and interrupt.
Could you just back up one slide and show us your last slide?
Yes.
So could you finish your sentence there? So for you, first of all, you said that R tends to 1 for all dimensions.
Yes, yes.
Okay,
Yes.
that was more or less the last thing you said, and then you have this other parent when k goes to infinity, but v max is fixed. I thought that was just as the same thing that you already said earlier. I'm puzzled as to why it's work in progress. You said for the uniform case.
Yes,
I
just
see.
for the last line is work.
I see. In the uniform case, not in the Bernoulli case.
And the number pi square over 8 is some one-dimensional or.
Yeah, that's the one-dimensional case.
Yes,
Right.
but this red box is actually any dimension.
Okay. Okay. Thanks. Just want to get that clear.
Any other questions? Going once? Going twice? Okay, thank you very much, Shiwen.